Now, up to now, I have not yet defined what kind of space I'm in yet. As long as I have a finite dimensional space, as long as I can find a set of basis functions, this is the same. But now to actually start to compute the A's and B's, we now need to specify what the basis functions are. And we started in the last lecture by defining a particularly convenient set of basis functions. That's the nodal basis functions, right? The definition of the nodal basis functions are that the linear combination coefficients are actually the value of the function at one particular node. So basically, if W is equal to a summation of I goes from 1 to n xi times wi, then xi is actually equal to I may have used a little bit of confusing notation because the xi's are not the spatial dimension, right? They are not the grid points. Basically, xi would be the value of the function at a particular, so let's say, let's say this is y. Oh, actually, can I just change the notation? Instead of saying it's a linear combination coefficients x, let's change it to maybe a. I used a before. Okay, so let's actually change to a, and so this would be, well, a is the actually bilinear form, right? So let's see. Let's see. Yeah, c is a good notation. So let's see. This is c, and now if this is a linear combination of ci times wi, then my ci would be actually equal to the value of the function at a particular xi. So this is x0, x1, etc. This is xn plus 1. Let's say we have n degrees of freedom, right? So this function also would satisfy the zero boundary condition, right? Which is required by our space, by our boundary condition. Okay? So this constraint uniquely defines the set of basis functions, and this is the basis function. It goes from 0 to 1 and then back to 0, and then stays 0 for the rest of the domain. So each basis function is going to be non-zero in how many elements, right? So let's say this is one element, this is another element. So each basis function is non-zero at 2 elements and 2 adjacent elements. Right, okay, so that makes the calculation a little bit later actually quite easier. Okay, so a few things to note is that the derivative of these functions are actually piecewise constants, right? The derivative of this function is actually a positive number in the left element and a negative number in the adjacent element on the right, and 0 in the, of course, 0 in the rest of the elements. So this is actually quite convenient because our a of wi, wj is actually defined as integral from 0 to 1. The derivative of the ith basis function times the derivative of the jth basis function. Okay. Now, first thing to note is that because both wi and wj has finite support, which means they are only non-zero in a small region in the space, in 2 elements. So most of these pairs are actually going to integrate to exactly 0, right? And the only pairs that doesn't integrate to 0 are what kind of pairs? Yes, they are the only ones that are not going to be 0 are pairs like this one and this one, right? These are not going to be integrating to 0. But if you have, for example, this one and this one, the gray pair actually is going to get you 0, a wi, wj, because they don't overlap, right? Okay, so the only ones that are non-zero are basically I minus j less or equal to 1, right? So if the difference between I and j are greater than 1, they automatically get to 0, because they don't overlap. Only if I and j are equal, or if I and j are neighbors, then they would actually integrate to something. Okay, so now let's look at the two different cases. One case is I minus j actually is equal to 1. So in which case, how many elements do they overlap? 1, right? If look at the red pair, right? So this function is actually 0 over here, while this function is actually 0 over here. So you only need to consider this interval or this element over which both functions are non-zero. And then what are the derivatives of these two functions? They are actually the same except for a sign difference, right? Because one goes from 0 to 1, the other goes from 1 to 0. So, and their derivative is what? It's actually 1 over the size of the element, right? So let me just define this size of the element as, let's say, delta x 1, for example, delta x 0, delta x 2, etc., up to delta x n. Okay, then this is actually what? It's actually, so first of all, this is constant, so the integral is actually the size of the domain, which is delta x, well, let me just say j minus I is equal to 0, so I can equal to 1. So basically the domain over which it overlaps is actually delta x j, right? So the bigger one, right? So because I defined x1 to be here, so delta x1 is on the wait, it's actually delta xi, right? So basically the if I'm looking at so this function is w1, this function would be w2, then I'm going to be looking at the overlapping region of delta x1, right? Okay, so it's the size of the integral, the domain length of the integral over which it is non-zero is delta xi. And the value of the function over which it is non-zero is minus 1 over delta xi square, right? Because one of them is 1 over delta xi, the other of it is minus 1 over delta xi. So this is it. Okay, and when I minus j is minus 1, of course it's the same thing, except you change the index I to j. The matrix is symmetric, right? I mean the A bilinear form is symmetric. Now the only last condition is I minus j, or I equal to j. So basically I'm going to be integrating the square of the derivative of a single basis function. And as we just said, there are two domains on which the derivative is non-zero. And in each of the domain, of course the derivative is a constant. So if I is equal to j, we are going to be integrating over the domain of I minus 1 and I, right? So, and the derivative in I minus 1 is 1 over delta x I minus 1, right? It's going to be squared and multiplied by the size of this domain because it's integral, delta x I minus 1. And then I need to add another element. And this other element, I have a derivative of minus delta xi, but because I'm squaring it, so the minus doesn't matter, right? So then it's multiplied by delta xi, the size of the domain. So that's the case when I is equal to j. Does it make sense? So let's actually conclude. I can also simplify this a little bit. So this cancels with one of these, so it's actually 1 over delta xi, and also this cancels, so it's 1 over delta xi minus 1 plus 1 over delta xi, right? Now what is my matrix? My matrix is going to be basically the first element is A W1 W1, right? So it's going to be 1 over delta x 0 plus 1 over delta x1, 1, right? The second, the 1, 2 entry is A of W1 and W2. So the value is minus 1 over x1, delta x1. And the value here is the same as its symmetric point. And here is 1 over delta x1 plus 1 over delta x2, etc., etc. And it's a tridiagonal matrix because all of the upper and lower diagonals away more than one entry away is equal to 0 completely. So this is going to be my matrix A. Does it make sense? It's the matrix that is composed of the pairwise basis function going into the bilinear form. Any questions? No? Okay. So then let's look at our B. So B is actually pretty easy, and let's actually take the special form of if f is a constant function 1, right? So let's solve this particular case first. So if f is a constant function and is equal to 1, then B is equal to the bilinear form, which is integral from 0 to 1 f times w I, right, dx. So if f is equal to 1, this is 1 and is simply the integral of the basis function. So what's the integral of the basis function? If the basis functions are hat functions like this.
Just delta x I.
If the delta x's are the same, right, then yes, you can put the area of the left triangle, sum it up with the area of the right triangle, it becomes delta x. But if delta x are not uniform, what's the area underneath the triangle, underneath the basis function? What's the integral of the basis function? Yes, it's basically the average of the two adjacent element sizes. So basically this one is delta x0 plus delta x1 divided by 2, delta x1 plus delta x2 divided by 2, etc. So actually I have a minus sign, right? So it's actually minus sign, etc., minus sign. Okay, so that's my right-hand side. Right, so basically the right-hand side consists of the application of the linear form on each of these basis functions.